Hi everybody, here's your warm-up. Please pause and solve. Okay, so finding the area under the curve means we are going to be integrating this function. So y equals the square root of x looks something like that. And on the interval from 1 to 4, that means we're finding the area of this region right here, which means I'm simply going to integrate from 1 to 4 square root of x dx, or x to the 1/2 dx. I bring this up a power, which brings me to x to the 3/2, and I divide by that power up front. I evaluate this from 1 to 4, and I get 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2, which gives me 2/3 times what the square root of 4 is 2 cubed is 8, minus 2/3. Okay, so if we really want to finish this, 16/3 minus 2/3, which is 14/3. I believe you could have stopped probably right here and been just fine. But if it is multiple choice, we do need to be able to get this simplified answer. So the reason we did this warm-up is because we are going to start reviewing volume. Specifically volumes of solids of revolution, and we're going to do these a few different ways, and then I'm going to come back and we're going to review volumes by cross-section. So first example I have relies on that function that we used in the warm-up, but now I want you to find the volume of the solid that we obtain when we rotate that region around the x-axis, specifically on the interval from x equals 1 to x equals 4. And so we calculate the volume by integrating the areas of the cross-sections. And I want you to think about this function from the warm-up and what shape the cross-sections are. And they are circles, yes. This function, if I go back to the warm-up slide, I guess I can't do that. Well, this function is entirely touching the axis of rotation. All right, I had something that looked like this. And so when this guy rotates around the x-axis, there isn't going to be a hole, okay? So the cross sections are going to be disks, which means the area of each of those cross sections is going to be pi r squared, and the radius is going to depend on the value of x. The radius is going to be the distance from the axis of rotation to the outside of that region, which is just going to be my function, square root of x. So the volume here is going to be pi times the integral from 1 to 4 of the radius squared. And I'm integrating that with respect to x. Okay? You've seen before that these are typically calculator questions. Now this is a very simple one because the square root of x squared just gives me x, and I can integrate this by hand very easily. For the sake of time, I'm not going to do that right now, but when we get to a more complicated example, I will remind you how to put these in the calculator. All right, second example. We're going to find the volume of the solid created by revolving the region between these two functions, y equals 2x plus 1 and y equals 1/2 x squared plus 1 around the x-axis. So here's what that region looks like, okay? The region enclosed by these two curves, and we're going to be rotating it around the x-axis. Now with this one, you can tell that there's going to be some space in the middle. When I rotate this region around, there's going to be a hole in the middle, which means the cross sections are not disks, they're washers. And so we have this inner radius and we have this outer radius that we need to take care of. So the outer radius is the one that's furthest from the axis of rotation. And remember, the axis of rotation in this case is the x-axis. So the outer radius is the distance between the further function and that axis, which in this case is the linear function to the axis. And we typically call that capital R. And then the inner radius is going to be the distance from the closer function to the axis of rotation. All right, and so we're going to call that little r. So in this case, my outer radius is going to be top minus bottom, 2x plus 1, minus bottom, which is just 0. And my inner radius is going to be that quadratic 0.5 x squared plus 1 minus bottom, which is just 0 again. And so the area of a cross section, again, if I have this washer and I want the area of the part that I'm shading in, it really does look like a donut, huh? All right, the area of that is going to be pi times the big R squared minus pi times the little r squared. I'm taking the area of the big circle and I'm subtracting the area of the little circle. I can factor out a pi, and so the area of one of my cross sections as a function of x is going to be pi times the little radius squared, sorry, the big radius squared, minus the little radius squared. Okay, and so my volume is going to be pi times the integral of the big radius squared minus the little radius squared. Now, all I'm missing are my limits of integration. And they didn't tell me what the what the bounds are on this volume, but we can figure it out based on where these two functions intersect. So what we're going to do is set them equal to each other and figure out where it is that they intersect. Now, it's pretty clear to me that they intersect at x equals 0. And I can plug in 0 for x, and I see that with both of these, when x is equal to 0, y is equal to 1. Oops. So that first limit of integration is going to be a 0. Now, the second time that they intersect, I'm going to do a little bit of side math over here. 2x plus 1 is equal to 0.5 x squared plus 1. I'm going to subtract 1 from each side, and I get 2x is equal to 1/2 x squared. And so obviously x equals 0 is a solution to this. I'm going to multiply both sides by 2, and I get 4x is equal to x squared. Yeah. And since I've taken care of the x equals 0 solution, I can in fact divide by x, and I get 4 is equal to x, and that is confirmed by what I see here. Okay, so my upper limit of integration is x equals 4. So I'm integrating from 0 to 4, big R squared minus little r squared with respect to x. Let's do this in the calculator. So everybody go ahead and get their calculators out, or pause and get one if you need it. I'm only going to do this one, but I do want to make sure that we're all getting better at using our calculators to integrate. So once you have your calculator out, you're going to go to Math. And remember, we're going to choose option 9, which is Fun Integral. And we're going to start by typing in the function that we want to integrate. And you're going to have to be really careful with parentheses here. I need to set a parentheses around my big R, which was, I believe, 2x plus 1, close the parentheses, squared, minus my little r, which was 0.5 x squared plus 1, close parentheses, squared. So what I have here is big R squared minus little r squared. All right, and that's my entire function. So, comma, with respect to x, comma, as x goes from 0, comma, to 4. And that's it. Okay, so the function, comma, the variable that you're integrating with respect to, comma, the lower limit, comma, the upper limit. And I hit enter, and my calculator thinks for a minute, and I get an answer of 44.8. Now remember, we did not put the pi in here, so you're going to have to throw pi at the end of your answer, 44.8 pi. If for some reason you need to write it as a fraction, you can go to math, and the very first thing is changing it to a fraction. So if you hit math, enter, enter, it'll change your answer to a fraction, 224 pi over 5. Okay. So in summary, if I'm rotating around the x-axis, you're always going to be integrating with respect to x. If the function touches the x-axis, you're going to be integrating disks. If it doesn't, you're going to integrate washers. Okay, and here I have pi times big R squared minus little r squared, where big R is the upper function and little r is the lower function. This is all if I'm just rotating around the x-axis. But as you guys have seen before, there are plenty of times when you're rotating around something other than the x-axis itself. So let's look at this example. We want to find the volume of the solid obtained by rotating the region between the graph of 9 minus x squared and the line y equals 12 on the interval from 0 to 3 about these three axes of rotation, the x-axis, the line y equals 12, and the line y equals 15. All right, so let's start by drawing a really good representation of this region so that we can use it for all three of these problems. Okay, so I know I'm only concerned with the first quadrant because I'm talking about the interval from 0 to 3. 9 minus x squared is a parabola, a downward facing parabola that hits the y-axis at 9 and the x-axis at 3. I don't know why I wrote x. Do you guys agree with that? Do you see where I'm getting that? When x is equal to 3, y is equal to 0. Okay, and then the line y equals 12 is going to be up here. Okay, and we're only interested in the interval from 0 to 3. So that means this guy right here is my region. All right, if I am rotating him around the x-axis, if that is my axis of rotation, then I'm going to be integrating washers. Because as this rotates around here, it's going to create sort of a, I'm not very good at drawing these. Well, there's the mirror image of it on the other side, and picture this guy kind of popping out the screen if you can, okay? And so I definitely have a hole in the middle, which means I need to think about this in terms of a big radius, which is going to be this one right here, and a small radius, which is going to be this one right here. Can you guys see that? So my integral that I'm going to set up is going to be pi times the integral from 0 to 3 of the big radius, which is just 12 minus 0, I'm going to call that 12 squared, minus the little radius, which is my quadratic minus 0. So minus 9 minus x squared minus 0 squared dx. All right? And again, I think at this point we can put in the calculator, we can get an answer. I want to just try and get through this setup of all of these. So I have my big radius, which is the distance between the axis and here, or sorry, 12 and the axis. And then my little radius, which is the distance between here and my axis of rotation. Okay, now we're going to use the same region, but rotate it around the line y equals 12. Which is one of the bounds of the region that I've created. Now I want you to picture this region rotating around that line y equals 12. It's going to do something like this. Yeah? Which means it is entirely touching the axis of rotation. There is no gap anywhere here, which means I'm not going to be doing washers. I'm going to be doing disks. This is actually going to be a pretty straightforward one. So I'm going to be doing pi times the integral of the big radius squared, and that's the only radius that there is. And that radius is just this distance here, the distance between the axis of rotation and as far out as I can go in my region. So we need to think of what this big R is in terms of top minus bottom. So this is going to be pi times the integral from 0 to 3 of what's top here is 12 minus what's bottom here is my quadratic, 9 minus x squared. squared. Don't forget that because we are doing circles here, pi r squared. And I'm going to integrate with respect to x. And that's it for this example because this is a disk, all right? It's been displaced up. We're not rotating around the axis like the actual x-axis. We're rotating around something parallel to it, but it's still just a disk. Here we go. Last example with this region, now we're going to be rotating around the line y equals 15. Okay, and so again, we have an axis of rotation that is parallel to the x-axis. I'm going to be going from left to right, so I'm still integrating with respect to x, but now I'm rotating around this region, which means that when this guy rotates around that whole thing, I'm going to get my mirror image somewhere up here. Can you kind of see that? And so we're going to have a gap here, which means we are going to be dealing with washers, which means I'm going to have pi times the integral of big R squared minus little r squared. Okay, and let's figure out what those are. Big R is the distance from the axis of rotation to the furthest piece of the region. So that's going to be this right here. Whereas little r is going to be the distance between the axis of rotation and kind of the end of the gap, which is right there. So let's put this together. I have pi times the integral from 0 to 3 of, I need lots of parentheses here, big R, top minus bottom. What's the top of R? 15. Minus the bottom of R is my quadratic, 9 minus x squared. These parentheses are important, guys. Squared minus little r, top minus bottom. The top is 15. The bottom is 12. Close those big parentheses, and this is integrated with respect to x. Okay, so that's every type of possible example you could see when we're integrating with respect to x. But I bet you're wondering what happens, what happens if what I want to do is integrate with respect to y. So here is another example. It's the same solid, well, it's based on the same solid that we were working with at the beginning of class. The region between y equals the square root of x, the y-axis, and the line y equals 2 around the y-axis. Okay, so this time I'm going to be rotating around the y-axis, which means I'm going to have my cross sections, I hope you can see those, perpendicular to the y-axis, which means I'm going to be integrating with respect to y, which means everything needs to be in terms of y values. Okay, let's do a straightforward one like this. My region is given to me as y equals the square root of x, but I don't want y in terms of x, I want x in terms of y. So x is going to equal what? Y squared. I square both sides, yes? So I'm going to have, because this is entirely touching the axis of rotation, I am going to be dealing with disks here. And so I'm going to have pi times the integral of my radius, which is just y squared, with respect to y, as y goes from what to what. And I can clearly see, given the bounds that I'm given, that y is going from 0 to 2. So even though x is going from 0 to 4, we're integrating with respect to y, which means I go from 0 to 2. Now let's do this in your calculator really fast just because I want to prove a point. Okay, when you bring up your calculator, I know that we were integrating with respect to y, but your calculator doesn't care about that. A variable is a variable as far as it's concerned. So I'm going to go to Math 9. And what I'm integrating is y to the 4th, but that doesn't matter, just call it x to the 4th. And then we're integrating with respect to x as x goes from 0 to 2. Okay? The reason your calculator doesn't care is if you said y to the 4th as y goes from 0 to 2, or x to the fourth as x goes from 0 to 2, or q to the fourth as q goes from 0 to 2. They're all the same thing. Okay, your calculator does not care. So this is what I get if I want it as a fraction. Math, enter, enter. And I get 32 pi over 5. Don't forget your pi. Okay. Let's do the same region, but rotate it around something that is parallel to the y-axis. Let's say x equals -2. I know this, oh boy. I know this is not to scale, but that's good enough. So this is going to be my axis of rotation, which means we're dealing with washers or discs. This is going to be a washers problem. Okay, my big radius is going to be the distance from the furthest point out to my axis of rotation, which is, I'm sorry if you can't see that, which is going to be this entire distance here. That's big R. And then little r is going to be the length of that gap. Okay, so this is going to be pi times the integral. Y is still going from 0 to 2. My big radius, instead of being top minus bottom, I'm right minus left. So this is going to be y squared minus, left is -2. Y squared minus -2 squared, minus my little radius is right minus left, 0 minus -2 squared. And this is dy. So I have pi times the integral from 0 to 2 of y squared plus 2 squared minus 0 minus -2 is 2 squared dy. One more with this. Let's instead rotate around the line x equals 4. See, I've tried to do one of every possible type of example here. All right, so x equals 4 is my axis of rotation, which means I am going to have a gap in the middle. And so I need to think about what is my big radius. That's that one. And then my small radius, again, is the length of that gap. So I'm going to have pi times the integral from 0 to 2 of big R, right minus left. Right is 4, left is 0. Big R does not depend on y in this case. So 4 minus 0 squared minus my gap, my little r, is going to be right minus left, 4 minus y squared squared with respect to y. Here's one final example. We're not going to go through the entire thing for the sake of time, but I do want to remind you that this is a possibility. I have the volume of the region obtained by rotating, the volume of the solid obtained by rotating the region y equals square root of x, the x-axis, x equals 1, and x equals 4 around the y-axis. Okay, and what I want you to realize is that, first of all, this is going to be washers. There's a gap. And big R and little r are going to sort of depend on where on this region I am. Do you see that right here, I'm going to have to split this because big R here is the distance between 4 and the axis, and little r is the distance between 1 and the axis. Whereas up here, big R is still the distance between 4 and the axis, but little r is the distance between this curve and the axis. So I'm going to have two integrals here. I'm going to have, for this first part, pi times the integral. And we're rotating around the y-axis. The cross-sections are perpendicular to y, which means this is going to be with respect to y. It appears that this goes from 0 to 1, and for the sake of time, we're just going to go with it, but really you would need to confirm that. 0 to 1. Big R is 4 minus 0 squared, minus little r is 1 minus 0 squared dy, plus pi times the integral from 1 to, I'm hoping that's 2, of my big radius, which is still 4 minus 0 squared, minus my little radius, which the gap is much bigger here. It's the distance between here and here, which is y squared minus 0 squared. So I don't see these come up often, but every now and then you're going to get one where you have to split the region. That is it. Here is homework number 1 for this section.